So for this example, separating variables, we get e to the y dy equals x dx, don't we? Integrate both sides, integrate the left hand side with respect to y. Integral of e to the y is according to our table of differentials, integrals e to the y, right, doesn't change. Integral of x, add 1 to the power, divide by the new power plus c. Is that implicit or explicit? Implicit, because it doesn't say y equals something. So this is our implicit solution. So let's try and get it explicitly now. So the left-hand side, what have I got to do to get y? Natural log of both sides, good. The natural log of e to the y is just y, is the natural log of the left-hand side, x squared over 2 plus c. So take natural log of both sides. In other words, y equals. There's nothing wrong with missing this step, you know. I know that the natural log of both sides is going to give me just y here, so I can jump straight from there to there. But I'm putting this in so that you can just to emphasize that in fact I've got two functions here that effectively cancel each other out, leaving just y. I can separate out this, I can call this natural log of x squared over 2 plus the natural log of c. Or I can call that the natural log of some constant ax squared over 2 multiplied, because if I've got to actually am I able to do that? So I can write it in these two ways, either of these two ways, given my explicit form. Now both of these two examples we've just looked at are what are called general solutions. So this example and the one we've just looked at are called general solutions because I haven't got a value for a. If I want a function that's going to model my particular situation, I need to find out the value of a to come up with what's called a particular solution. And I also need to be able to talk about the range, as we said at the beginning, the range of values over which these functions will work.